Previously, we saw that the fact that all observers have to agree on the same speed of light has forced us to rethink our ideas about simultaneity, and also to recognize that different observers will have different experiences of space and time. One of the things that we saw was that moving meter sticks are short, which means that if we look at someone else's meter stick moving in front of us and we measure with ours, it's shorter. Now, to that person, that meter stick is 1 meter long, and there's nothing wrong with it because they're having a different experience of space than we are. But what this does mean is that between observers, length is no longer an invariant. And so this tells us that the Galilean transformation is also incorrect and that we need to revisit it. So the substitute for the Galilean transformation is what's called the Lorentz Transformation. And again, a trick that physicists, that special theoreticians do, is when something has been working really well for quite a while, you don't just automatically chuck it out altogether. You see if there's some way that you can patch it up. So in this case here, let's think about our observers S and S prime. And we'll say that at t equals t prime equals 0, so all of our observers are sine o'clock, right at the origin, we emit a light pulse. Now our observer S prime is moving relative to S with velocity v. So at some later time, we'll let this be S's coordinate system here at time t. S prime's coordinate system will be out here at time t, and we'll say this coordinate system is moving to the right at velocity v. Now we're going to be very careful here and say that this is S prime's coordinate system at time t prime. This is because since we also saw that time dilation was a thing, we know that S and S prime's clocks will now be disagreeing with each other. We can rig it up so that they agreed with each other at time 0, right when the light pulse was emitted at the origin, but that's it. So our light pulse will have traveled at the speed of light, and since we will eventually find that nothing can go faster than the speed of light, that means the light pulse is to the right, is in front of the origin to both observers here on the right side. So we can measure the position of the pulse at these times. Now S, we'll say that the x-coordinate of our light pulse here is x, and S prime is going to say that it is x prime, because remember, S prime being an observer, they're welcome to say that they are stationary and that's S who's moving. So they can look at this and say, alrighty then, my origin is here, the pulse is there. So far, nothing different than what we would be doing with the Galilean transformation. In fact, the idea was that since the Galilean transformation worked really well, as long as you weren't going crazy fast fractions of the speed of light, maybe there wasn't all that much wrong with it. And so this much right here would be the Galilean transformation to relate x to x prime. And here I'm having to use a t prime, whereas before with the Galilean transformation, we just said t and t prime were equal. So that's the first thing we have to do to be careful. And then the second thing is that we'll just insert some fudge factor. We'll call it capital K. And we'll try to solve for this fudge factor. And similarly, we can take the inverse transformation to get, if we know the x-coordinate, we want to get that S measures. We want to get the X prime coordinate that S prime measures. We can write the same thing. We'll just assume we need that same fudge factor. Then we'll put in X minus VT here. And again, we have to be careful about our T and T prime, because now we know that they will have to disagree. But since both observers agree on the speed of light, we can also note that x is equal to the speed of light times the time in their frame. And for s prime, x prime will be equal to the speed of light times the time in their frame. All right, so it's a whole bunch of tedious algebra, and I'm going to skip over the tedious algebra here. So I'll just observe lots of algebra. And one of the first things that pops out is that our fudge factor turns out to be our friend gamma. And if we go ahead and make that substitution in, we can now say that x prime is equal to gamma x minus vt, and x is equal to gamma x prime plus vt. So the old rule of thumb of change the primes, change the sign still works. But now we also pick up, because we had to solve for t and t prime along the way, we pick up an additional set of transformations for the measured time. There. We now also get that t prime is equal to gamma times t minus vx over c squared, and that t turns out obeys the change the primes, change the signs principle, t prime plus vx prime over c squared. So this is what's known as the Lorentz transformation. And the first thing is, whoops, I need a prime right there. So the first thing to notice is that at low speeds, if v is much less than the speed of light, let's take a look at what happens to our t and t prime. If v is much less than the speed of light, this term here is going to be basically zero. Because if I have a number that's a lot less than c, and then I'm just plain dividing by c squared, I'm going to get basically zero. Ditto here. So that gives us, when things are moving slow, that t and t prime are basically the same. So in the limit of things going slow, we've already worked out that gamma is basically 1, and t prime will be basically the same. And so we recover the Galilean transformation where in the regime where it worked. Remember, key thing with the correspondence principle is we have to show that the new model is that the old model is a limiting case of the new model where the old model worked. So if our speeds are slow compared to the speed of light, we do indeed get the Galilean transformations back out. Now, it does turn out that this is going to affect our velocity transformations. In the Galilean transformation, we could just simply add and subtract velocities. So say if somebody was driving down the highway at 100 kilometers an hour and you passed them at going 110 kilometers an hour, they would say that you were going at 10 kilometers an hour relative to them, just subtracting out the speed of the frame. Turns out that we're not going to be quite so lucky here. Now, since, just as a reminder, since v is used for the velocity of s prime with respect to s, we use u for the velocities that s measures of some object, and u prime is the velocity that s prime would measure for some object. So let's go and figure out what we get here. So u prime, now here we have to be very careful. How are they going to measure velocity? Well, they're going to differentiate the position they measure with respect to the time they measure. So this is going to be dx prime dt prime. So if I'm going to want to try to get this into something that looks like a u here, what I'm going to be doing is differentiating this expression here, but this is going to give me a dx, this expression here. This is going to give me a dx dt prime that I need to be careful about. So let's just take care of this problem right away by doing the chain rule. So this is going to give me dx prime dt 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 prime. All right, so now I can go ahead and differentiate x prime with respect to t, and then this works out. So this is going to give me, taking this term here and differentiating with respect to t, not t prime now, I'm going to get gamma, which is a constant. Now dx dt, that's u. dx dt prime would not have been u. That would have been something else. But dx dt is u, so that works. Minus, well, we need to differentiate this. This is just going to be minus v. Okay, so far so good. This is looking kind of Galilean transform-ish if that gamma weren't there. Now we have to also differentiate this t with respect to t prime, but that works out. We've got a prime variable here, and we've got a prime variable here. So everything's in the land of primes when we do that. So differentiating this term here, the t with respect to t prime, that's going to give me another gamma, which is a constant. dt prime is just 1. V is a constant. X prime, when differentiated with respect to t prime, that's u prime. So I get u prime v, and then c is a constant, so c squared. All right. I can clean this up just ever so slightly to note that I have a gamma squared sitting there. And then I have u minus v, 1 plus u prime v over c squared. All right, but we remember, so let's just do this in a different color here. We remember that gamma is 1 over the square root of 1 minus v squared over c squared. So if I square that, gamma squared is 1 over 1 minus v squared over c squared. If I multiply top and bottom by c squared, that'll give me c squared over c squared minus v squared. So I'm going to go ahead and substitute that in for gamma squared here. So now my expression for u prime is c squared over c squared minus v squared, u minus v, 1 plus u prime v over c squared. All right. And again, it's just going to be some more algebra to get there. So I'll just say some more algebra. We end up that with u prime is equal to u minus v over 1 minus uv over c squared. So if we didn't have the stuff in the denominator, we would have the Galilean transformation. So again, checking with the correspondence principle, if v is much less than c, then this term is basically 0, and I do end up with the Galilean transformation. The inverse transformation still follows the rule of thumb of change the primes, change the signs. u will equal u prime plus v over 1 plus u prime v over c squared. So those are the velocity addition formulas. If we didn't have the denominators, we would have the Galilean transformation. If things are going slow with respect to the speed of light, this correction term basically goes to 0, and we recover the Galilean transformation. Now, the other sanity check we can do is to make sure that all observers agree on the same speed of light. So let's say that you observe some photon traveling by. So we'll say we're throwing a photon, even though that doesn't really make sense. Instead of, say, throwing a ball or something. So we'll just say light goes past our observer S. S measures the speed of that light to be c, which they jolly well better. Let's see what S prime measures. S prime would say, okay, u prime is u plus v over 1 plus u prime, u prime is u minus v over 1 minus uv over c squared. Now we said that u is equal to c, so in this case, that's just for this example. So this is c minus v over 1 minus cv over c squared. We can cancel 1c. If I multiply top and bottom by c, this is going to be c times c minus v over multiplying the bottom by c, c minus v. Cancel out, and sure enough, S prime also measures that the photon is traveling at the speed of light, which is totally what we should expect. So now, what if you're going at some relativistic speed in between? So we've been thinking about characters skateboarding, but I don't think even Tony Hawk, as awesome as he is this awesome. So I think this is going to this is a job that's going to call for a monster here. So we're going to have Elmo on his skateboard throwing a baseball. Now, on his skateboard is going at 0.75 of the speed of light. This is why I figure that Tony Hawk couldn't handle this. Just the air resistance alone should just completely demolish him. So, of course, we have Elmo's friend Zoe sitting off by the side of the road here, watching Elmo throw the baseball. So Elmo is throwing a baseball off of the skateboard at 0.5 of the speed of light. So we want to know, how fast is Zoe going to see the ball going? Well, our first step is to figure out who's S and who's S prime. So in the problem, the narrator is always rooting for somebody. In this case, the narrator seems to be implying that Zoe is the one that the narrator thinks is stationary. So Zoe gets to be S, which means that we are asking for what the velocity of the baseball is that Zoe measures. So then that means that this is u prime here, because Elmo is our observer S prime. So we can figure that out. U is going to be u prime plus v over 1 plus u prime v over c squared. So we will get that this is 0.5c plus 0.75c over 1 plus 0.5c 0.75c over c squared. So the c's cancel out. This cancels one power of c, that cancels the other one. And if you grind it out, you get that u is equal to 0.909 c. The Galilean transformation would have predicted 1.25 c greater than the speed of light, which can't be the case ever. So why is it, though, that that Zoe measures it to be 0.909 rather than 1.25? Go ahead, pause the video, and come up with an explanation for that. Okay, so what Zoe is going to say is that Elmo's meter stick is short and that his clock is running slow. Both of these are going to conspire to effectively give a bigger speed in Elmo's frame than Zoe would say is merited. Now, keep in mind, in Elmo's world, there's absolutely nothing wrong with his meter stick. There's absolutely nothing wrong with his clock. The meter stick is 1 meter long. The clock is ticking over 1 second per second. Elmo and Zoe are having different experiences of space and time here. But using the moving meter sticks are short and moving clocks run slow, this explains why to Zoe that it wouldn't be 1.25 but would be something less, like 0.909. And by the way, let's just copy this real quick. If you were to do this problem with Elmo throwing the baseball to his left, there we go. So let me just adjust that right there. So if Elmo throws the baseball to his left at 0.5 c, there we go, then we would be saying that u prime is minus 0.5 c. And because this is a velocity, we do have to take into account the directions. So when Zoe measures this will be minus 0.5 c plus 0.75 c over 1 plus a negative 0.5 c, 0.75 c over c squared. And so in this case here, it turns out that you get plus 0.4 c, which is faster than what you would have expected from the Galilean transformation. From the Galilean transformation, you would have expected it to just be 0.25 c to the right that Zoe would have seen. But instead, it's 0.4, and the reason it's 0.4 again is because Zoe would say that Elmo's meter stick is short and that his clock is running slow. Alrighty. So in the next video, we will continue along our merry way of finding things that need to be corrected. It turns out that we will have to make corrections to our definitions of momentum and energy. And then we will finally get to E equals mc squared. So catch you in the next video.